Well, good morning. How are we? Chalk. Well, I was going through the book of one of your colleagues, and I realized that people did not take the notes about the capacitor networks, which I well explained. So you're supposed to take these notes. Eh? You are supposed to take those notes. Capacitors in series and capacitors in parallel. But when I was going through an individual's note, I didn't see that. So those people, you are supposed to pass the other side now, because at the end of the day, you're exhibiting another character. Pass this way. Why do all people want to pass close to the camera? Supposed to pass this way. Excuse me. So after having energy stored in a capacitor, energy stored in a capacitor. Now I am saying make sure that you have summarized notes of capacitor networks made by you yourself. The good thing, you have access to the books, handouts, and the library. Or else, of course, we would want so much to treat you like O-level students. But because we do believe that you are a little advanced, and nobody is here and was forced actually to be here. So let us try to have the notes when we are tasked to do so. Energy stored in a capacitor. You people have started my lesson. Now you are coming in and out. You are disorganizing me, to be honest. You are disorganizing me, which is not proper. The bell was rung some minutes ago. So for today, I am not allowing any other person to enter. For today, I am not allowing any other person to enter. So I've said nobody is going to enter today. Now, before you guys, the movements are too many. I don't know why it takes you people so long to get organized. I'm not allowing anybody, please. Honestly, I am not allowing anybody to enter. Honestly, I am not allowing any other person to enter. Are you a physicist? Yeah. Because now I think I should treat you the same way I treat the senior twos. If I enter in class, nobody else is supposed to enter, maybe unless you are a teacher. Otherwise, people come in and see you inside, they go out. Then they come back. That one is not proper. Simply sit, wait for the teacher, and then go. Ah. Higher levels of disorganizations, I want to assure you, they cause poor performance. Ah. Now, senior 5 science, from today onwards, once you find me in class, look for another class. I repeat, it's on record. Once you find me in class, look for another class. Otherwise, we cannot have scientists who are this level of disorganization. No. Somebody finds you in class, goes out, comes back again, goes out, comes back. That is one. Two, if you don't have a calculator, you are not a potential candidate of my class. Am I communicating? If you don't have a calculator, you are not a potential candidate of this class. You are misplaced. Because there is no way you can keep asking for help from the neighborhood. So those are two general ground rules. One, once you find me in class, look for another class. Two, if you come without a calculator, still I will make you go out of class. Because now if we don't take a step of seriousness, people will keep thinking that physics is just passable like any other subject. I think that is clear. Let's remind ourselves, how did we define physics in senior 1? How did you define physics in S1? Huh? The study. Good. You had a different idea? It is simply a branch of science that deals with two things. One, matter. Two, energy. So anything that can do work, because again, if I try to remind you, what was work? What is work? Please tell me. So now you are mad at me because I've given the rules. Talk to me, human, what is work? Yes. Work is a product of force and distance. And work is literally, I'm good, sir. Work is literally the energy. Energy is the ability to, meaning if you can do work, you are energetic. So anything that can do work has the energy. That's why we are looking at the energy stored in a capacitor, because a capacitor can do electric work. Are we together? So we are trying to bring the principles that we studied some 3 years ago, trying to reapply them in other concepts. Are we together? So work being the ability to do work, energy being the ability to do work, and work is force times distance. It means that even work in a capacitor involves moving something that does it from one point to another. Human, I have sounded a warning. The next time you find me in class, you look for another class. I only meet you once, so put it in your programs. Every Monday after break, I am here, isn't it? So every Monday after break, if it means to forego the break, forego it. Yes, it's just a matter of time, 2 years. So energy stored in a capacitor. I've said we are going to look at the movements of the charge moving from one point to another. If it moves from one point to another, it has done work, because work is a product of force and what? And distance. So anything that can be transferred from one point to another, it means work has been done. And once work is done, it means it has not been wasted. You remember the principle of conservation of the energy. How does it state? Energy can neither be created nor destroyed, but it can change from one form to another. So if I pick this person from here to here, I shall have done work. And the energy I will have used to transfer him from a point to here won't be wasted. It will be stored in him. And that energy can also do another work. So you can say, suppose the PD between suppose the PD between the plates at some instant was V. Suppose the PD between the plates at some instant was V. Suppose the PD between the plates at some instant was V. Suppose the PD between the plates at some instant was V, full stop, or a comma. When a small charge of plus small charge 2, when a small charge is transferred from the negative plate, to the positive plate, when a small positive 2 is transferred from the negative plate to a positive plate. Of course, when charge is transferred from one plate to another, it will have increased the PD between the plate. So we say the PD increases by a small change in V. The PD increases by a small value of V. The PD increases by a small value of V. Therefore, on a new line, work done to transfer charge. Therefore, work done to transfer charge. Because a small charge was transferred from one point to another, and when it was transferred, it increased the PD that was there by a small value V. So a small work done will be the PD that was there times, it is actually equivalent to the PD plus the small change that was there, then times the small charge. When we are looking at the work done in transferring charge from one point to another, we say that it equals to, that work done was equivalent to, you don't remember, it was Q. Work done well by from first principles, Work done is force times the distance. But the work done that we looked at under electrostatics was the charge times speed. Is it what we said? So if this speed was there and a small work is done, a small work will be the PD that was there plus the one that it increased to, and then times the charge that brought the increment. Are we together? Then you expand the brackets. When I fall down, you laugh. This is so if you expand this, you will have small work done equals V small charge plus small v small what? Charge. So when you multiply two very small numbers, what do you get? You get what? Your mathematics is magwamped. When you multiply two small numbers, you get a very much smaller number. Check. You are arguing with a mathematician from Makerere University. When you yes, you check there with your computer, 0.0001 times 0.00001, what do you get? You get 0.0000, a very much smaller number. Hey, you people, you think I am consulting you or I am informing you? When you multiply two very small numbers, the product tends to zero. What do you get? So if you compare that and those two, which one is smaller? No, why are you arguing? You think me, I studied from, I don't want to mention people's universities here. Think me, I studied from around here. I went to the best university in Uganda. Well, is the determinant. But it sent me to the university. Do you think it will send you to the university? Okay, so what am I trying to drive to is this one here will tend to zero. Are we together? So we shall have that the small work done is approximately V times a small change in charge. Having explained this, so don't ask, but why are you ignoring this? I have said a product of two human. A product of two very small numbers gives you a much smaller, so that number tends to zero. So this one here tends to zero. You're asking how? Okay. Pardon? The letter? Which one? Small. This one is a symbol meaning is small. This one, a small change. Delta. It's called delta. In mathematics, you will do differentiation from first principles, yes? Sigma? It is okay. It can be a sigma, it can be a delta. In mathematics, when we are dealing with this unit of maths is called calculus, where you do differentiations and integration. Have you done differentiation yet? And from first principles, and you don't know this or this, So it's the same thing. Eh? So how do you read this? Then this, a small change, of which the two are changes. Am I clear, man? So don't get confused of the symbols. Are we together? So I am saying that the small work done is approximately equal to the PD that was there, because the product of the small PD that increased and the small charge tends to zero. So we shall have an expression that looks like this. I mean, that looks like this, which we are going to integrate. But now here, I am going to go through the integration as a marathon. After you have looked at it in pure maths, that's when you now come back and revisit your physics and see whether it makes mathematical sense. Because now for me, I'm not a maths teacher. Pardon? I did maths, but I did not major in maths. So we can continue and say, but V equals Q over C. So if we substitute it there, physics is like CRE. All right, so we substitute there, we shall have our work done. Our small work done equals Q over C times the small change in charge. Now, if we have a number of small work done, a small work done plus a small work done plus a small work done, are you sure? When you add a number of small figures, what do you get? I think you get a big figure. Your mathematics. Your mathematics. Well, but you will be fine. So I am saying it is only when you multiply two small numbers that you get a much smaller. It tends to zero. But the addition of smaller gives you something big, man. In Uganda, we have a saying that 1 by 1 makes a bundle. Hey, do you think it is in Runyankole? How would you state that in Angola? Eh? Kamwe kamwene kakora omuganda. That is actually translation. It is what? 1 by 1 makes a bundle. It's in. So if we add small work done plus a small work done, what we shall be doing is actually integrating. So if you integrate the small work done, you get a big work done, which is also Q over C dQ. So we are saying that total work done to charge the capacitor, will be the integral of from 0 to a charge 2 of Q out of C divided by V. Now, are we together? Human. Your face looks a little. The gesture shows that you are not okay with this elongated S. That's why I said I am going to take you through this a marathon when my colleague Oroma, isn't he the one? Matthew teaches you calculus 1 or 2. Calculus 1. Calculus 1 is integration differentiation. I don't remember. So you will see that an elongated S is a sign of integration. So we are adding small work done plus small work done plus small work done to get the total work done, which is a W. Now on this other one, we are going to integrate all the expressions with respect to Q. Now, of course, he will have to teach you what we call functions, integrating a function with respect to a variable. But that one is not in my field. So allow me go straight to the final expression. When he teaches you that mathematics, you will come back and check for the mathematical facts. Is it clear? So when we integrate, we shall have this equaling to a half q squared. Let me first check I don't make a mistake. Q squared over C. But Q equals, is it CV? Right? So our work done, convince yourselves that it is a half C V squared. Yeah? What? So somebody is asking, where is the D? Where is the D? That is between this Q and the other Q. We are integrating a function Q with respect to X, dx. So the dx is the, how can I call it? It is the term that brings about the fact that the integral is with respect to X. We are going to integrate all those functions that are having Q as a variable. Yeah. Squared is only on V. Of course, you can try to check if after I've done the integration here, if after I've done the integration here, I get this. That one I've said Oroma will further explain the mathematics. Eh? I've said Mr. Oroma will further explain. But now I am interested in what you get after integrate. If you substitute for Q here, you will get this. You can also check and see whether it's what you get. Is it what you get? Check. What do you say maybe? Check and see whether it's what you get. Substitute for Q with CV. But remember, Q has been squared. Is it correct? Human, is it correct? When I tell you to try it aside and you keep looking at me as if I'm the one who is going to sit for the exams, I don't understand you. Can't you people do substitution? If I have work done equals Q squared over C, but Q equals CV, if I square Q, I square both sides here. Then I tell you to try some work aside, you people take it serious. Otherwise, me, I will come here and I lecture. So this becomes C squared, V squared, isn't it? Now, when you substitute this back here, you'll have work done equals C squared, V squared over 2C. This one cancels with the square. And you remain with your work done as a half. The C is alone, V is squared. Even doing that work aside, you cannot. Human, remove this thing here. Well, now what are you doing? Yet I've done it on board. You want to show me that now you can do it? Even doing aside mathematics, you don't want. All right, examples. Or say NB before you write the examples. NB, the energy stored per unit volume, NB, the energy stored per unit volume the energy stored per unit volume equals the energy stored per unit volume equals the energy stored per unit volume equals so the energy is a half CV squared and volume equals the area times the separation. So when we substitute these two back here, we shall have a half CV squared over a what? Over AD, which is CV squared over 2AD. And this is the energy per unit what? Per unit volume of a parallel plate capacitor. Examples. Example 1. The figure below shows a network of capacitors. The figure below shows a network of capacitors connected. The figure below shows a network of capacitors connected to a 10 volts battery. Connected to a 10 volts battery. Full stop. Calculate the total energy stored in the network. Calculate the total energy stored in the network. Calculate the total energy stored in the network. You completely refused to fasten the board. You're waiting for injuries. So the capacitor network is as below. So that is the network. Our task is to find the total energy stored in the whole system. The noise means we are done with the drawing. Let's go through the solution. So can we try to analyze the problem or the network problem? Of course, now in this case, the arrangement of the capacitors is mixed up, right? There are those that are in parallel, then there are those that are in C, but we deal with them accordingly. We don't simply come and say one in parallel, another one in series, then we deal with them as if they are in series. So first and foremost, to determine the flow of charge from the source. When this charge flows like this and it reaches here, right? When it reaches the capacitor of capacitance 5 microfarad, the whole charge, the total charge that was supplied by the source is going to go through the capacitor, right? And then it will move to the other side. Then it continues to flow. Is it clear? Then when it meets a junction, some charge will go this way, another charge will go this other side. The moment you achieve that, then that means that at the junction, those ones are in what? In parallel. Then you continue. Part of charge will go this way, part of charge will go this other side. When the one that has gone this way, it reaches a junction. Are we together? It also splits, which means that also those ones are in what? In parallel. So that charge will go through this and then this. Are we together? Then the charge that went down this way, it is the same charge that will go through this one here. Is it the case? Huh? So if it is the same charge, it means that the two are in what? Are in what? Are in what, please? So if they are in series, how do we get the effective capacitance? What do we add? When they are in series, we add the C1 plus C2. You see? Is it what we said? Is it what we said, you people at the back? Capacitance of two capacitors in series is C1 plus C2. But it's what you are telling me. So the capacitance of these two, actually I'm beginning with these two because the same charge that came through this goes through that, right? So this and this are in C, so I combine them. When you combine them, what do you get as their effective capacitance? Add, please, do it there. People who are looking at me, I will chase you. I must be doing something. As the effective. Are you sure? Instead of following the procedure, you are pressing a calculator. Can you write in your paper and show me 1 plus C equals 1 plus C1 plus 1 out of C2? You people, you are pressing a calculator giving me very wrong answers. And you are confident, by the way. You man, try it aside. That's what I'm asking for. Get a pen and a paper, try to see what you get the effective as the effective. You're holding a computer as if you're experts. Maybe I should start coming here, talk as I want, then I leave. Because at the end of the day, when I give you chance to also try, you don't want. How will you master the concepts if you don't want to practice? So these two, the effective is 4. Now where are you getting the 0.25? Because you think you can press it on a calculator. So we have agreed that these two are in series because the charge that goes through this is the same charge that goes through the other one. Now, what you get here, if I can try to reduce it now, if I remove this, because the effective is what? So I can put the effective 4 micro F. Now, the charge that went through this is not the same as the charge that went through this, but it is going to move out as the same charge as it went into the junction. This is what I'm meaning. The charge that went through this, because remember, we started from the source. It came from the source to a 5 microfarad capacitor. At the end of the day, I tell him to do work, he looks at me as a sheep. You man, you stand up. Be there. Now, we started from here. So it flew from here to the 5. And the 5 has no junction. So the all charge went through the 5. And then it exceeded here, it came here. When it reached here, it found a junction. Some went down, another one went the other side, which means that all the capacitors that they are going to find in the different directions are in parallel. So we ignored this first, then we continued with this. The one that went through this as Q may be 1, it went through this and it met a junction. When it met a junction, part of it moved downwards, another one it moved this way. So the one that moved here, it met 2 capacitors, which were in C. Now we have found the effective of the 2, which is what? Now, if the charge that entered here split into 2, and when it reached here, it came back as the way it went in, it means these 2 are in what? In what? So what is the effective C of 2 capacitors in parallel? How do we get the effective capacitance of 2 capacitors in parallel? Find out. You find it. You might be writing from there. They are what? 6. Now again, I'm going to reduce that. Are we together? Are we together? So I reduce this because this 2 forms 1 whose capacitance is 6. So I remove this. I put it here. 6 microfarad. Again, we continue. Charge came from here, flew to this. It went through because there is no junction. It met a junction. Part of it went that side. Stand up as well. The one at the wall. Yeah, you'll be writing from the standing position. So we are here. Part went this way. Another one, it came here. So the one that went this way moved, and then it also moved through this, isn't it? So if it is the same charge through this and this, the 2 are in what? Are in what? How do we get the capacitance of 2 capacitors in series? Find it. What do we get? 2 points. Again, allow me to reduce them and I put in 1, right? So I rub this and I leave this. So this and this, they have formed what? 2.4 microfarad. All right. Again, we come back. Charge started from here, went. If you don't find a junction, you assume that that charge went through wholesomely, right? So it met this, no junction. So it went through wholesomely. Then it reached here, it found a junction. Part went this way, and then I am not seeing any other capacitor. So meaning that the one that went this way passed through that capacitor or went onto that wholesomely. Then it reached here, but remember there is this one that also branched off from here. It is supposed to meet this such that when they come back here, they come as the way they left or it left. So now we don't have any other this way. Now let's come and consider the one that passed here. Are we together? So the one that is here, it met this and there was no junction. So it went through wholesomely. Now when it reached here, there is a junction. Are we together? Part went this way and another one went this way. The one that went this way, it only met one capacitor, and the one that went downwards also met one kappa, which means that they are two sharing charge, which means they are in what? Parallel. This one took part of the charge and this one took part of the charge. So they are in par. So what is the effective capacitance there? Pardon? 12. So allow me also remove the 2 and I remain with 1. So I'll remove this. And I remain with 12 microfarad. Again, we continue. Charge comes from here, flows to this, no junction. It goes through wholesomely. Then it reaches here, it finds a junction, part moves downwards and the other one goes the other side. The one that goes the other side, we have already seen that it goes through one capacitor. So that one has no the network. So we come to this. We have this and this. We have this and this. And the charge that goes through the 3 does not branch anywhere. It goes through the 12. Is it? So what arrangement is that? Series. What is the effective? Huh? Are you sure? So I am rubbing off 1 here. Are we together? If I rub off 1 here, 2.4 microfarad. Now, again we come back. Are you getting something? When it flows from the source to a capacitor, no junction, it goes through wholesomely. It meets a branch point. Part of it goes this way, another part moves downwards. The one that moves this way goes through one capacitor. Then it flows to the point. Then even this that goes through the other side goes through one capacitor. Are we together? Which means that there are 2 in par. What is the effective? 4.8. Again, allow me to remove this. Allow me to remove this. And I remain with this. 4.8 microfarad. Again, I come back to the source. When charge is produced here, it flows to this, no branch. It goes through wholesomely. Then it continues, it meets this, no branch. Again, it goes through whole summary and it comes back to the source. So the two are in what? In what? What is the effective? Two point. So allow me remove this. Pardon? All right. Now, if you have C as 2.45 microfarad, you have V as 10 volts. Can't you find E? Huh? From E equals what? A half CV squared. So E will be a half times 2.45 exponent negative 6 times 10 squared, such that your E is young girl, be pressing your computer. Don't sit and look at me like that. I hate that. You don't have a computer? You are risking. What do you have? Pardon? This is 2.45 exponent negative 6. You have 1.225 what? What is the unit of energy? Joules. Take note. Yes? Is CV squared, eh? I think the best way is for you to start that number afresh. Don't simply copy what I have on board. I just wanted to make you understand step by step. So as you are taking your notes, write it afresh. Every two capacitors you discover their arrangement and you substitute for their effective, you redraw the circuit. For every two capacitors you discover their arrangement, you redraw the circuit. Hurry up, hurry up. This thing is micro. You write a U. Let me teach you how to write letters. You write a U, then you give it a long tail on the other side. When you try one, that is micro. Where is your physics book? Are you doing something or you are just buying time? I have a number of examples here to do. When you be on that one for so long, I'll leave the rest for you people. For every two capacitors whose effective capacitance you have got, redraw the circuit and substitute them with one. That's when you'll understand it. The moment you identify two and their arrangement, find their effective, then you replace the two with one. Keep doing that until when you remain with one capacitor in the circuit. Get me a calculator. Continue. If I get one candidate finishing, I will go to another thing. Which ones are you starting with?
No, you first resolved these ones.
Good.
Then I did this and this. They got 6.
Whichever two you do, you redraw the circuit. That's when you will enjoy it. Whichever two you finish, now like this one, you redraw the circuit. That's when you will understand it the more. Every two capacitors, you identify their network, you redraw the circuit. You started with which one and which one? This is the mother figure. So you did this and got 4, which is this. Then you took 4 and 2, 6. Here. Every two you do, redraw the circuit. Let me see the mother figure. It's this one. So you started with which one and which one?
This one.
I point at the two that I started with this, and I formed this from here.
From here,
I
started with this one.
And these two, and they formed a 4. Then from here, from here, which two did you take to get now what you have? You took this and this. Oh, you don't know?
Oh, you know? You took this and this, or this one?
You got this.
Yes. Then I got this and this.
Which one?
This one and this one. Then I went on this one.
First, wait. This and this.
Yeah.
6 and 6 they gave you?
4.
So you will have 12, but then there is this. 3.
Yeah, this and this one.
Series. This is 12 and
3
2.4. So you have this, these two, this and this. So which one and which one are you considering now?
This one I will consider. This one. I'll first consider this one and this one.
You are lying. If you consider this and this, then the junction here.
Even so, yeah.
Because there is a junction here, having a capacitor this way and this one. So these two are in what? So you consider those two first, such that you curb this charge into one. make sure that by the end of your energy, they told me this figure is wrong. Somebody said there that this figure is wrong. Is it wrong? You got it. Yeah, so make sure that at the end of the struggle, you have this as the yield. Human, you are comfortably seated. I don't know whether you are getting the correct things. If you don't want to intervene, me to intervene, it's okay. We are still on one example, guys. Can we hurry up? Well, let me look at yours. Don't stretch. Show me from here to here. I consider this and that. Please point at the capacitors that you consider. First and foremost, where have you seen a connection that does not add up? Do I have a connection there that does not reach the wire? Uh-huh. Which one? Mm. Mm. Good. I said when you consider two, you redraw the circuit. Mm. They become parallel to this one. This way you add this one and the other one. Came to this one, to bring this one. Just the door and just the door. So came from this one. Did you get what was here and the combination of this? Then I will get it later. This and this one. Yeah. They are in parallel. So they giving me but this is 6 and this is 6. Giving me 2. Then after getting this one, which is this one will be say yeah. After getting this one, I don't answer here because I have it better. When I come later here, getting the information. This one they are in series. I will have to show this one and this one. Which I also in series. You are lying. This one and which she gonna play this one, the combination of this one and this one. To be a problem. The combination of this and all of this is in what? The combination of this to be series. Then the combination of the all of this and all of this is in what? There is a junction here. The all of this and the all of this can't be in series. There is a junction here already that shows you that what you get here and what you get here, they are sharing. Part of the charge goes this way, part of the charge moves downward. So what you get here and here, they are in parallel. If I get this one and this one, which are in parallel, I will get this combination. Then this one, which are also in parallel. Now the whole of this, you want to say it is in parallel with this one? Is that one parallel? You people are taking a lot of my time solving one problem. Have you finished? My daughter, have you finished? Now, me, I have many examples to solve. You write and say a 47 microfarad capacitor. A 47. Example 2. A 47 microfarad capacitor is used to power a flash gun. A 47 microfarad capacitor is used to power the flash gun of a camera. A 47 microfarad capacitor is used to power a flash gun of a camera, full stop. The average power output of the gun, is 4.0. The average power, a flash gun of a camera, full stop. The average power output of the gun is 4.0 kilowatts. The average power output of the gun is 4.0 kilowatts. For a duration of the flash, for a duration of the flash, which is 2.0 milliseconds. 2.0 milliseconds. 2.0 milliseconds. Full stop. Calculate the Roman 1. Calculate the Roman 1. Potential difference between the terminals. Potential difference between the terminals of the capacitor. Potential difference between the terminals of the capacitor. Potential difference between the terminals of the capacitor immediately before a flash. Potential difference between the terminals of the capacitor immediately before the flash. Roman 2. The maximum charge stored by the capacitor. Maximum charge stored by the capacitor. Roman 3. The average current provided by the capacitor during a flash. Average current provided by the capacitor during the flash. I rub off this. So now here, we may not necessarily come up with a circuit. We may not come up with a circuit diagram, but we are going to analyze, remind ourselves of some principles. Where are the prisoners? Aren't you part of them? You man, stand up. You're a prisoner of war. Shouldn't sit down until I tell you to do so. So we are going to remind ourselves of the principles and some laws. Then we apply them in this case, some definitions, and we come up with a solution. So analysis or solution. What do we know, ladies and gentlemen, out of the problem? We know the power as what? 4.0 kilowatts. What else? The capacitance as what? 47 microfarads. Next, the duration time T, 2.0 milliseconds. Next, that is all. What do we need? Roman 1, the PDV. Now, from this information that we know, remember a gun was used and it flashed. When it flashed, I told you sometime back here about the cameramen of those days who used to use, or whose the cameras were using the capacitors that can be charged, take a pic, flash, and they are discharged. Are we together? But now this one did that, but it had been electrically charged, having a given power. Are we together? So now, what principle are we going to apply in this case? Which principle are we going to apply in this case? Yes? Come on, speak louder. The principle of conservation of what? Which states that energy can neither be created nor destroyed, but can be transformed from one form to another. Ladies and gentlemen, not even God can create the energy. These are not my words. These are words of the principle. Are we together? Not even who? God can create what? Me, I'm a Christian. I believe that he can. But the principle is saying no. Are we together? So which energy was converted from one form to another? The electrical energy of the gun was converted to the electrical of the gun to electrical of the capacitor. So the energy, the mechanical energy is, I think, if we have the power P, power P is going to be the work done out of the time what? Where the work done is the energy, right? So we shall have the energy here, energy E equals power times what? Times the time. This is the energy by the gun. Oh, are we together? Then the energy by a capacitor is a half CV squared. So these two were not created, neither were they destroyed, but they were conserved. So it means that the energy of the gun which was lost equals the energy of the capacitor. So we shall have the energy as P times T equals a half CV what? Squared. Are we together? The power is 4.0 kilowatt. So we shall have 4.0 times 10 to power 3. Is it the case? Times T, which is what? 2.0 times 10 to power a negative 3. Milli is a prefix that represents 10 to power a negative 3. Equals a half times the capacitance, which is 47 exponent negative, times the V we are looking for, but what? Squared. Are we together? So please, you squeeze this. I think this will cancel with that. You have 4.0 times 2 as 8 equals 2 times 47 exponent, equals a half negative 6 V squared. So V squared is going to be 8 times 2 divide 47 exponent negative 6. All right? Am I correct? Yeah. Mm-hmm. Man, check. That's what we're supposed to be doing, checking for all those algebraic errors that you can get. Some of you have issues with using a computer. So press correctly. Follow.
Good morning, sir.
Yes, sir.
Those who have not shaved the hair,
I told them they must shave the way I shaved.
no, they said deliberately they have refused 1, 2, 3.
So me, I have not your I am not a lawyer or scientist. When they point you, you march out. You will come back later.
So I request towards when you are, I don't want to interrupt you with your lesson.
Yes, sir.
Towards the end of the lesson, just because I can see the danger zone is here.
After we are done, they are just doing algebraic work. You can take them now. The rest of the work they can do it even after.
Ladies and gentlemen, good morning, good afternoon, boss can work. As I touch
Of course, as the Afanda is doing his work, also continue. If they take you, you go and serve the country. How fair, how not fair am I? This school has rules and regulations. You want me to violate them?
but now, teacher,
Yes, sir.
this one is being a gentle class, and another class, and you read it by example.
Yes, sir.
That's give them only today. Then tomorrow you come back.
Appreciate the funding.
I also want when I'm not happy. When you see me not laughing, that means I'm annoyed.
And you must trim off the same hairstyle like the teacher.
Can you plan what is happening? Somebody's having that t-shirt you are at.
Okay, can you finish up? Can you finish up, please? No, I am under. He's my boss. You want me to again say no to the boss? Do you know this is the job I have? This is where my family is getting a living. So you want me to? How would you want me to again say no to the? I just surrender because Roman 2. I rub off. Yeah, that is what life is all about. So this is my job. You want me to violate the rules of the job? How? Don't you know that you're supposed to trim off the hair? If me, a teacher, I trimmed off the hair, what about you, a student? I trimmed off during the right time. Didn't you have the weekend? Pana, use a razor blade, man. So Roman 2, I rub off this. Roman 2. Roman 2 is asking for the maximum charge. So Q equals CV. Q equals what? Is it CV? From C equals Q over V. Q equals CV. So Q will be C is 47 exponent what? Negative 6 times V. What was V? 583.5. 4, 6. What do you get? Pardon? 2. People are already doubting that. But the man was reading the same thing, only in exponents. 0 point? Like that. Coulombs. Then Roman 3. Current. How do we get the current in electricity? Current equals charge out of what? Time. We have the charge, we have the time. Right? We have the charge, we have the time. What do you have as I? Pardon? Uh-uh, 1.35 from where? This is the charge, and the time is here. Eh?
You don't have the stand. Those ones who have the side stand up have come back again.
I will go by 13.5.
Now the side, don't. Hello? Don't remove that stand. That's the punishment now. So don't come. I'm going to treat you just separately. Just now, you just put on, I know where to take you. You come over my friend. Well, I'm not with you now.
Okay, you can write. Do you remember? Can we come back? Do you remember the example that we did as 1, which had a battery of 12 volts? Check your notes. And it had 2 capacitors, 2 and 3, which were in parallel. You remember that? And another one of 5. Yeah? Do you remember that? Do you have that circuit? You add a question that calculate the total energy stored in the capacitor network. On that circuit, you're going to do it as an exercise, but the question is calculate the total energy stored in the capacitor network. I have said that circuit where we had the 2 capacitors, 1 of 2 micro and 3 being in parallel. Yes, do it as an exercise, but the task is calculate the total energy stored in the capacitor network. Calculate the total energy stored in the capacitor. When I'm giving notes, some people don't want to write. Now I'm referring to the notes. That capacitor, that circuit, calculate the total energy stored in the capacitor network. That is 1. 2. Again, there is a circuit diagram that has 2 capacitors, 1 of 4, another one is of 1. Then the 2 micro and the 2 micro with 120 PD. Calculate the energy in the 1 microfarad capacitor. Calculate the energy stored in the 1 microfarad capacitor. I've left 2 items. 2 what? I've said refer to the circuit diagrams that we drew. Calculate the energy stored in a 1 microfarad capacitor. You can start now. I beg to stop there.